keep your mics muted and do not put on your video because network issues are there, of course. Okay, so now I will start. Okay. Okay, so this is your the heading of your module, Mathematical Physics 1, Vector Algebra and Vector Calculus. This is the name of your course and paper. PHS is for Physics, A is for Honors, CC1 is this paper, CC11 is this Mathematical Physics 1, and TH stands for Theory. All right. So in total, you have 50 marks in this paper, out of which 10 is, of course, your internal assessment. All right. So I'll start today's class by asking you a question, and it's a very, very easy question. So my question to you is, define a vector. Very easy question. All of you have gone through vectors. So can someone please unmute and tell me the answer? How do we define a vector?
Quantities which have magnitude and directions are called a vector, which also follows the parallelogram rule of addition.
Okay, very good. Anyone else? Everyone agrees with that definition? So
Yes.
I'll just write what she said. So answer to this is a physical quantity that has both magnitude and direction. And she also added the point that which follow the parallelogram law of addition. Not only that, it follows also the triangle law of addition. So the definition, please unmute whoever has unmuted, please mute yourself. I should not have to repeat this so many times. So the definition of vectors that we learnt in school was that a physical quantity that has both magnitude and direction is called a vector. So we were learning physics and science, and suddenly in class 9 we were told that, see, all these quantities that you are learning about, all well and good, but see, they can be categorized into two groups. One group which have only magnitude and direction is irrelevant, for example mass and volume, they are called scalars, while the other group like displacement or force or velocity, for which not only the magnitude but also the direction becomes important, and if you do not say something about the direction, then the whole thing becomes irrelevant. Those quantities are called vectors. Okay. Now, before moving ahead with vectors, I will ask you another question, and you might think that's irrelevant, but even if you think irrelevant, I'll still ask you the question. Okay. And my question is about electric current. Okay. So is electric current a scalar or a vector?
Scalar, ma'am.
Scalar.
Scalar.
Everyone agrees with that? Scalar.
Yes, ma'am.
Okay. So let's find a slide on the definition of electric current. So electric current is limit delta t tends to 0, delta q by delta change of electric charge, where q is the electric charge, right? So obviously there is no vector in it, there is no vector quantity in the definition, and so obviously it is a scalar quantity, right? Now, constitutes an electric current? Please do not, the next time someone unmutes when I do not ask a question, without my asking a question, I will have to remove that person from the meeting. So what constitutes an electric current? When a current flows from one point to another, know that there is which we call the negative potential, and there is a dearth of electrons at the other point, which we call the positive potential. More electrons, negative, less electrons, positive, and electrons, yes, and electrons move the point where there are more electrons to the point where there are less electrons. But conventionally, we take the direction of current on the other, in the other direction, right, in the opposite direction. So definitely there is a direction associated with the flow of current, with the flow of charges. We have charges moving in a particular direction and we have current moving in the opposite direction. And only then will we constitute an electric current. It is only when charges move in a certain direction that we say that a current flows. So even though it is associated with a particular direction, yet current cannot be called a vector. Why? Because it is not a vector, because it is a scalar, that's it. Okay, you don't need to go very deep to think why current is not a vector, because it is a scalar, simple. So I will give a new definition of vectors which you have already given. So along with the statement that a physical quantity that has both magnitude and direction, I will also add what you said is that physical quantities that have both magnitude and direction and obey the laws of vector addition. Not only the parallelogram law, but also the triangle law of vector addition. Okay, so when you are asked to define a vector, if you are after in your written or in your oral question, you have to say this entire, say the laws of vector. Okay, so you see what we are doing in this class is recapitulating what you already know, but already know from our school level syllabus. Next, what we'll do is we see how a vector may be represented. Now, this representation is not what we see in print. You know that in print, when we write a vector, we write a letter and we give an arrowhead on the top of it, which will mean that we are denoting a vector quantity. Or sometimes in a book, if the quantity is printed in bold, it means that we are talking about a vector. So that's not what I'm talking about. In general, there are two ways in which you can represent a vector. Okay, first is the geometrical representation. Okay, so this again all of you know. This is what I'm talking about. A line segment with an arrowhead. So the tail is the starting point, the head is the ending point. The length of this line segment is called the magnitude of the vector, and the arrow will give you the direction of the vector. Okay, so when you have a line segment with that kind of representation is called a geometrical representation. Okay, and suppose you have a vector A like this. So this line segment gives the mag of A and arrow gives the direction of A. And you have another vector B. So as you can see that B points in a different direction and has a dude. And then someone asks you what
I'm sorry to interrupt, ma'am, but you are completely inaudible.
Yes, ma'am, we cannot hear you.
Ma'am, your Skype mic is off.
Can you hear me now? Is this better?
Yes,
Yes,
ma'am.
Yes, ma'am.
yes,
This
ma'am.
is better.
Okay. Okay, fine. So where were we? Yeah. Okay. So basically, I was discussing something that you already know very well, that we can very conveniently displace vectors parallelly and then apply the law of vector addition, the triangle law of vector addition, and find the resultant of two vectors A and B. In the same manner, if someone asks you what is the value of A minus B, again, you can similarly take the vectors, displace them parallelly, and then take the vector B and just rotate it by 180 degree to get the minus b vector and again apply the triangle law to get the new resultant C prime. So all this you already, and I did not bother to write down the triangle law or the parallelogram law of vector addition or the formula for the magnitude of the vector, you know, the a square plus b square plus 2ab cos theta kind of formula, because you all know things from your high school vector knowledge, and you can get readily available in any mathematical methods book. So I just want you to realize that all this that you knew already, this kind of representation of a vector. Now you might think that why am I emphasizing on this? Because there is a second of representation, that is the combination. And I'm sure all of you know how to write a vector in a component form. Still, I will want to tell you how the components arise. Okay, so I am stressing on the basic of the thing that you. So for this, what we do is we take a coordinate axis and we name them x, y, and the point at which all the axes meet is called O, the origin of the coordinate system. This kind of a coordinate system is called the Cartesian coordinate system. Okay, where the axes x, y, and z are mutually perpendicular. Now, at this point of time, I'm missing my classroom a lot, because when I do this in the classroom, when I'm face to face with the students, I quickly tell them to look at the corner of the room and see where the two walls and the ceiling, or the two walls and the floor meet. So that is the best example of how a coordinate system is formed, a rectangular Cartesian coordinate system. So if you are sitting in a rectangular room, then please do look at the corner of the ceiling or the floor to see how the three planes, this plane here, and the floor or maybe the ceiling, how they intersect each other to form the coordinate system. Okay. And before moving on to the component representation, I would also like to tell you that, remember, this is not a unique coordinate system. This is only a special kind of coordinate system that we are presently using for our convenience. Okay? There are several other kinds of coordinate systems which we will encounter later on and will study in detail too. So for the time being, for our convenience, we are using the rectangular Cartesian. So here, let's suppose we have a vector A which starts at the origin, ends at the point ax, ay, az. Okay, so this vector it could be anywhere. We could have parallelly displaced it and brought it to this position. Just remember that it is arbitrarily placed. Okay, so you have to imagine here a 3D picture where x, y, and z are perpendicular to each other, and A is a vector arbitrarily directed in space. Clear? Now what we do is, okay, so this is what I already said. So now we drop a perpendicular from this point A, ay, az onto the xy. Now x is 0. So the value of the point, the coordinates at this point is ax, ay, 0. And from this point again, ax, ay, 0, we draw perpendicular x, a, y, a, z, we drop a perpendicular to the z axis. Okay, so these are the intercepts. So this portion here is the intercept on the x-axis, we call it ax. The intercept on the y-axis is called ay, and the intercept on the z-axis is called az. Okay, now let the vector A make an angle alpha with the x-axis, angle beta with the y-axis, and angle gamma with the z-axis. So just as I told you, the vector A is arbitrarily directed in space so that at this particular direction, orientation rather, the angles that it makes with the three coordinate axes are alpha, beta, and gamma. Okay. Then we can write ax equal to mod a cos alpha, ay equal to mod a cos beta, and az equal to mod a cos gamma. Okay, where mod a, by mod a I mean the magnitude of the given vector. And these three quantities, cosines of alpha, beta, and gamma, are called the direction cosines. All right. You can show that cos square alpha plus cos square beta plus cos square gamma is equal to 1. These quantities ax, ay, and az are the components of the vector A along the three axes. So this is how we get the components of the vector along the three axes. Cartesian coordinates in the Cartesian system. So these are the Cartesian components. In a different coordinate system, they would have different values. Okay, and we can write vector A equal to x, x cap plus ay, y cap plus az, z cap, where x cap, y cap, and z cap are the unit vectors along the three axes. Okay, so this is how we can represent a vector in the component form. So we saw how we represent a vector in the geometrical form, and now we saw how we can represent a vector in the component form. Okay. Now we just said x cap, y cap, and z cap are called the unit vectors. Is someone trying to say something? Because I cannot see the Skype chat right now since I am presenting the PPT file. If you have to say something, you have to unmute and say.
Hello, madam. When we
Yes.
divide the vector by the modulus of the vector, magnitude of the vector, then we get the unit vector of this particular vector is defined as the direction of the vector.
Right. So a vector, a unit vector is a vector in a given direction which has unit magnitude. So direction remains the same, only the magnitude becomes unity. So for any given vector, we can write unit vector in that direction is the vector divided by the magnitude of that vector. All right. So in the Cartesian system, the unit vectors along the three axes are denoted by x cap, y cap, z cap, or more popularly I cap, j cap, k cap. And the most important thing that you have to remember is that these three unit vectors form a basis or a complete set of vectors in the three-dimensional Euclidean space, because you can express any given vector in terms of these unit vectors. This is a very, very important concept. Why do the Cartesian unit vectors form a complete set? They form a complete set, or sometimes we say they form a basis, because any vector in the Cartesian system can be expressed in terms of I cap, j cap and k cap. Clear? Now, two things that I want you to note at this point is that when I represent a vector geometrically, it helps us in visualizing the vector. Okay. So for example, I tell you that this vector here that I've drawn for it, say, has magnitude 10 newtons and it is directed from east to west. So quickly you can visualize. So, okay, a force which has a magnitude of 10 newtons. So it is quite a strong force and it is directed from east to west. Okay. Or say I tell you that I am drawing a vector whose magnitude is say 200 kilometers and it is directed from Calcutta towards southwest. So you can quickly imagine, okay, so probably ma'am is talking about some place like Kharagpur or some place down south, which is about 200 kilometers from Calcutta. Okay, so it gives you a visualization at once. However, working on with pen and paper, using this visualization is not very convenient. So when you need to do problems, then just the line segment with the arrowhead is not of much use. You can use the triangle formula or the parallelogram formula, but for that the algebraic or component representation becomes much more convenient. Why? For example, see, suppose a vector A in the component form is written as ax I cap plus ay j cap plus az k cap, and another vector B in the component form is written as bx I cap plus by j cap plus bz k cap. Then if you are asked to add A and B, even if you do not know the geometric representation, you can quickly do this. So A plus or minus B, vector addition, is simply scalar addition of the coefficients of I, j and k. So even if you are asked to add 100 vectors, all represented in the Cartesian component form, you can do that in a jiffy, because all you need to do is add algebraically the coefficients. You need to gather the coefficients of I, j and k and add them. Okay, so this is much more convenient. So whereas the geometric representation helps in visualizing the vector, the component representation helps in calculation. Okay, so this is why I was emphasizing on how the vectors are represented in the two ways. Okay, after this what we are going to do is talk a little bit about linear dependence and independence of vectors. This again is a very important concept that you need to have. Suppose we have a set of vectors A, B, C, etc. E, F, G, H, whatever. Okay. And we have a set of scalars, small a, small b, small c. So all the small alphabets are scalars and all the capital alphabets with arrowheads are vectors. Then if it is possible to write this kind of a relation, okay, then we say that the vectors are linearly dependent. If it cannot be written, they are called linearly independent. So, definition of linear dependence or independence is this. If we have a set of vectors and a set of scalars such that any one of the vectors may be expressed as the linear combination of the others, then they form a set of linearly dependent vectors. See, over here in this equation, you can take any one vector to the right hand side and it can be represented as a linear combination of all the other vectors. So they are all dependent. But if you cannot do it, they are independent. Okay. For example, I cap, J cap, and K cap. Can you tell me whether they are independent or dependent? Yes? What? কি বললে আমি শুনতে পেলাম না। Do you want me to repeat this once more?
ম্যাম জানি না তো কি করব।
Just now I told you that if they can be written as a combination, they are dependent. If they cannot be written as a combination, they are independent. Unit vectors I cap, J cap, K cap. আমরা লিখতে পারি কি I cap equal to some 2 K cap plus 3 J cap? কখনো লিখতে পারি না। I cap, J cap and K cap, one cannot be written as a linear combination of the other two. So they are independent. And why is this important? It is important because a set of vectors can form the coordinate axis of a coordinate system only if they are linearly independent. That is why I have emphasized on this portion. I've kept a single slide on this. In books, you will find only the definition. Okay, but I am emphasizing on this because you need to know why linear dependence and independence are important. It is important because a set of vectors can form. So if you are given, say, 3 vectors and asked, can these vectors form the coordinate axis of a coordinate system? How will you find out? You will see whether you can write the vectors as a linear combination like this, whether adding together the vectors give you 0, a null vector. If you can do it, then they are dependent. You cannot form a coordinate system. If you cannot do it, then they are independent. You can form a coordinate system. Okay, so this is very important. The last thing that I'm going to do in today's class is rotation of coordinate axis. Okay, so suppose you have, now this I'll do for 2 dimensions. Suppose you have the xy coordinate axis and we have a vector OP starting at O and ending at P. All right, I haven't given the arrowhead, but this red line represents a vector. Now I draw perpendiculars from the point P onto the x and y axis at the points Q and R respectively. All right, so OQ is the x component and OR is the y component. Now what I do is I rotate the coordinate system. Okay, so I rotate the system by an angle phi so that new position of x axis is x prime and new position of y axis is y prime. Okay, but the vector remains the same. The vector OP, I do not change it. It remains the same. I only rotate the coordinate axis. So now when I draw perpendiculars from P onto the coordinate axis, the new perpendiculars become PQ prime and PR prime. So the new components become OQ prime and OR prime. All right. So this is the vector R, and we consider anti-clockwise rotation of the xy coordinate by an angle phi, keeping R fixed as I told you. So from this very simple trigonometry, you can see that we can write OQ prime, which is the new x component, as x cos phi plus y sin phi, and OR prime is minus x sin phi plus y cos phi. So in general, when the frame, the coordinate frame is rotated by an angle phi, the new components are given by this ax cos phi plus ay sin phi, and ay prime is minus ax sin phi plus ay cos phi. So the vector does not change under such a rotation. Only the components change. And using these new components, you can carry on with the vector in any form that you want. You have to remember that if a quantity S does not depend on the orientation of the coordinate axis, then it is called a scalar. Here you see that though the vector does not change, but its components do change under rotation of the axis. So such a quantity is a vector. If the quantity does not depend on the orientation, whatever be the orientation of the axis, the value remains the same, then it will be called a scalar. Okay, so I will end my today's class here. In our next class, as I told you, we'll start with product of two vectors.